give a round of applause to CEO of Astria, Josh Bowen. Thank you.
Okay. Are we good? Okay. Hi, everyone. So I'm Josh. I'm the CEO of Astria. We're building the shared sequencing network. So my talk is on shared sequencing, speedrunning the endgame, and we're going to have to go pretty quick through the talk since I've got 45 slides, so that fits. So first to start, like, what's a sequencer? When we say what is, a sequencer, I think there's a lot of different definitions you could possibly use. That's open to debate, but for this talk, as we talk about it, we're going to assume there's 3 components in the stack of like a roll-up and really like a blockchain in general. We're going to have a mempool, and I'm going to say that is an unordered bag of transactions. We're not getting into what the peer-to-peer interfaces are and whatnot. It's just a bag of transactions. You order those transactions, that is a block, and then you execute those transactions. That results in a new state DB with a resultant state root. So when we say we have these 3 components, the sequencer is dealing with the second step, and we would say an executor, or whatever term you want to use, for the third step. And we are really just focusing on the second one here. So why would we have a sequencer? Specifically, why would you have a sequencer in a roll-up system, right? We're aware of based roll-up designs and how you could do that. But our argument is you just have a sequencer because you want speed, or really end users want speed. And there is this inherent state where, like, once a UX has been offered to an end user, they're not going to want to use something that is slower than what can be offered by a competitor. So this is my argument for what is like a minimum viable roll-up architecture at like a very, very broad abstraction. You have a user, they submit transactions to a sequencer for the roll-up. That roll-up is responsible for batching and then submitting those batches to a data availability layer. The user will get a soft commitment from the roll-up sequencer, and then when the transactions or the batch of transactions is included on the data availability layer, they're going to get a firm commitment. And this is really the state of, I know this is a Cosmos conference, but this is very Ethereum focused, right? This is the state of the existing rollups on mainnet Ethereum, right? Users do, in fact, get fast confirmations from these sequencers, but this comes at the cost of decentralization, because right now we have sequencing nodes run by a single party, generally the development entity that is building the given rollup. So what's a shared sequencer? What do I mean by about the kind of idea of being shared? Kind of expanding the previous diagram we had, we propose that you have a single shared sequencer, or more accurately, like a shared sequencer network. That's what we're representing by having multiple boxes here, right? This shared sequencer network has a leader rotation, but multiple rollups can utilize a single shared sequencer. And so a user would submit transactions to a roll-up RPC. This is standard flow as like Optimism, Arbitrum, whatever. But the roll-up nodes would then be responsible for submitting these transactions into the shared sequencer, which would produce an ordering. And that is where a soft commitment would be given back to a user. And then a batch would still be submitted to a data availability layer. And then users would once again get a firm commitment from that data availability layer. So what do we kind of argue about like a shared sequencer? Why does this thing exist? It's because we want to be decentralized by default. I think someone else in an earlier talk, maybe Caleb, was talking about this progressive decentralization aspect. This has kind of been the sales pitch of rollups to date. But the reality is we haven't gotten to the decentralized part of it, right? We're going on 18 to 24 months of mainnet for rollups, and they're still run by a single centralized node run by the team. Our argument is that if we see many, many rollups, whether it's hundreds, whether it's thousands, whether it's tens of thousands, each of them can't afford to go through this process of launching in a centralized manner, then becoming decentralized over some kind of hand-wavy timeline. So these things need to launch and be decentralized by default. At Astria, we kind of think about MEV as like a first principles approach to building these systems. So we consider ourselves using MEV-driven design, and that'll be expanded on in this talk. And this really becomes, paraphrasing Hasu from Flashbots, is like really it's all PBS. Like all of these architectures of rollups in general trend towards PBS-style designs. Okay, so this is what I'm arguing. This is an MEV supply chain for a rollup using like a centralized sequencer right now, right? You have a user, they send a transaction to an RPC, that goes into the rollup's mempool, that is going to go to a searcher, and that searcher is going to create a bundle, bundle goes to a builder, builder generates blocks, that goes to the rollup proposer, in this case there is one proposer, this is when a soft commitment happens, batches go to data availability layer. So I'm going to have to go pretty quick here. I got 9.5 minutes, and we got 30 slides to go through. So if we want to do a shared sequencer, how we're going to abstract this, we're going to replace the rollup RPC stays there. The rollup mempool is going to be replaced with a shared sequencer mempool. The rollup proposer is going to be replaced with a shared sequencer proposer. Otherwise, this supply chain looks pretty similar for one rollup, right? We can compare these really quickly here. Really, we just replaced 2 of the red boxes with the blue boxes, right? Moving on from this, okay, come on. Right, if we want to compare this, so let's say we have a red rollup and a green rollup, right? If we want to have 2 of these, we need to have this MEV supply chain exist twice, and all of the components in it are duplicated, right? This is kind of undesirable for various reasons. We don't want people standing up this infrastructure multiple times for multiple rollups. Maybe this works when we have 5 rollups. Probably doesn't work when we have 100 rollups, right? You use a shared sequencer for this, and this is kind of expanding, right? We have multiple rollup RPCs submitting in the shared sequencer mempool. That mempool is being looked at by searchers across multiple rollups, right? So the searchers look at one mempool interface, and they can see transactions proposed for multiple rollups. Then those, again, have bundles. Those go to builders, blocks, shared sequencer proposer, batches, data availability layer, right? So what is a shared sequencer? When we look at it in this kind of MEV-driven design space, right? Really, it's a single place where these block builders within this PBS MEV stack can settle multiple rollups within a single kind of synchronous time window, right? And I know, like, settlement layer, right? This is a term. What we mean when we say settlement in crypto means many, many things. Stop saying settlement layer, but fundamentally, this is what we're doing here, right? What's kind of a trade-off here, or something we want to think about in this design, is that shared sequencers potentially lead to super builders. And what do we mean by super builders? If we go again into the same flow, MEV supply chain, multiple rollups, one mempool, searchers, builders looking in the same mempool, feeding into the one shared sequencer proposer. Really quickly summarizing PBS, the key thing here is that the proposer is the one that has a monopoly on the ordering rights of the next block, right? They get to make the decision. They're kind of the monopoly actor in this economic system. So if we expand this into what we might see an actual larger MEV picture look like, rollup RPCs, maybe they feed into their own rollup mempool, as opposed to having a shared sequencer mempool, and maybe we have some searchers that are interacting with one specific rollups mempool, because fundamentally searching is like an arbitrage game, and it's very specialized, right? That's why we have PBS in the first place, because validators are not wanting to be specialized actors searching for arbitrage opportunities. But these people may specialize to only look at one rollup. They may also look at some multiple rollups, and we would consider that a cross-chain searcher. But then we look at this builder thing. Fundamentally, a shared sequencer only has one block for multiple rollups, and that means you have one builder that's constructed an economically optimal block for bundles coming from multiple rollups. Some of these bundles might be for a single rollup, some of them might be for multiple rollups, right? And what this results in is we end up with Ken Griffiths building all the blocks for all of the rollups using a shared sequencer. For those that don't know, if there's not MEV talk, Ken Griffiths is the CEO of like Citadel, right? TradFi, like quant trading stuff. What about composability? What do we get from that when we do this, right? Is the composability atomic? That's an argument we make. There is inclusion that is atomic because you have one node that is choosing the order of blocks for multiple rollups, right? Again, going back to this diagram, what is happening here in the flow between a mempool and a block being actually proposed, right? The really key component here is the bundles, right? What is actually existing in a bundle that a searcher looking at a mempool, again, from one rollup or many rollups, and generating a bundle that goes to a builder to result the block, right? We argue a bundle is equivalent to a native shared sequencer transaction, right? So if we look at this flow, right, we have a bundle, and we're going to argue that a blue block is from, or a blue transaction from one rollup, a red transaction from a different rollup. When these go into a shared sequencer transaction, fundamentally it's one transaction that is signed and thus is only valid within the rules of the shared sequencer if it includes the bytes of both rollup transactions, right? This is where you get your atomic composability. It is an if and only if both transactions have been included. It is not within the purview of the shared sequencer proposer to separate out one transaction from the other. The shared sequencer block would then consist of a chain, or rather a series of these shared sequencer transactions. And then when the rollup wants to actually execute this, right, that last step from the earlier diagram, they will pull out the relevant transactions from the transaction within the shared sequencer, right? So who creates bundles, right? again, go back to this large expanded diagram here. We're looking at these searchers, right? They're the party responsible for creating bundles. And really, we're going to simplify to looking at cross-chain searchers because that's the more kind of interesting component, right? A searcher looking at one rollup is kind of bog standard. That's what's happening right now on Ethereum. So then we can expand this to look at what is the fundamental order flow that is going to a searcher. There's been an argument made that really what defines a searcher versus a builder. The searcher is someone who has better order flow than someone else, and therefore allows them to find more opportunities for arbitrage. We can see this kind of being expanded beyond the scope of this talk, but we see order flow auctions and stuff like this. But I'm just going to make the argument that there might be some component, Suave, or something else like Suave, where users submit their transactions to, and this may be doing an order flow auction, but somehow these cross-chain searchers are retrieving order flow, these raw signed transactions by a user. And so then they're actually responsible for creating it. And so this goes into what I'm going to argue is the end game. And this is going to be hotels, trains, and intents. And so this is a reference to the hotel and train problem. And what the hotel and train problem is the idea of you want to go to a city. You need to book a hotel in that city, and you also need to book a train ticket to that city. How do you ensure that you only get a hotel if you've also booked a train ticket, or a train ticket if you've also booked a hotel? Because different people are selling you the hotel and the train ticket. And if one of those transactions fails, then you might have already kind of committed yourself to one of these without having the other go through. This is where the atomic inclusion is really, really valuable, right? You purchase the hotel only if you have also purchased the train ticket and vice versa, right? If we expand this, again, we're simplifying this kind of MEV supply chain. We'll say the user is always submitting all their transactions to Suave or something. This is some kind of meta mempool. Maybe it is optimized for various flows for searchers. But what we've kind of done here, right, is we've called the searchers solvers now. And this is because this is in the design space of intents, wherein a user may not be submitting a transaction, where in a transaction we're actually going to call that an execution trace, which means a specific set of state transitions that must occur on a state machine, and they sign over that execution trace. Really what a user wants to say is, I want to buy a hotel, and I want to buy a train ticket. And I don't really care how on the back end that got executed. This is what I want to do, and I want a solver to determine what is the best execution trace for me to accomplish that intent, right? And that bundle, right, of this hotel and train ticket still going to go to this builder, potentially a super builder here, but we still have a simpler flow. And then that goes, again, shared sequencer proposer, and then that gets batched, right? Come on. But really the key thing here, right, is how are users figuring out intents? There's been a lot of proposals for intents. Some of them, proposed by Suave, is the idea that an intent, or really in their terms a preference expression, right, would be a smart contract on Ethereum. We don't believe that users are going to assemble a specific smart contract to specify their intent at the time they want to make this purchase. Someone is going to have to abstract this away for them. So the really missing piece here in this overall flow is some user interface with which a user interacts that is then generating an intent that goes into this Suave or something box, right? The order flow goes to a solver. They generate an execution trace. Execution trace is a bundle that goes to a super builder. That super builder gives a block, shared sequence proposer, data availability layer. So we've gotten a pretty wide range, but this is actually what I believe is kind of the necessary set of components in a system to provide an end user a good user experience while having a highly scalable stack of components. What does this all relate to at this kind of UI level? What are the important things to keep in mind here? Fundamentally, we're going to say aggregation theory. This is an idea generally promoted by Ben Thompson from Stratechery. It's the idea that whoever controls the flow, right, the input area where a user is interacting, that's going to be the sticky component, and that's going to drive a lot of the system. So really the thing we want to think about and what we want to see is potentially, well, do we want to see, or what we should be mindful of kind of when we look at these designs is the idea that there might be a single UI that interacts with multiple chains, but overall produces one block, and all of this kind of relates to that architecture we had. So I know this is very quick, but we got 45 seconds left, and that was my last slide. Again, I'm Josh. I'm the CEO at Astria.org. We are building a shared sequencer network. We are doing this in a MEV-driven way, and so we're thinking about a lot of these things from first principles. If you want to get in touch, our Twitter is Astria.org. My Twitter is JSkyBowen, or you can find me here for the next few hours.